Welcome to the deep dive. Ready to dive deep into the world of fluid dynamics? We're going to be looking at some interview excerpts about Bernoulli's equation that you sent in.
Oh, this is going to be fun. Sounds like this interview really put someone's knowledge to the test.
Yeah, it does. We're going to break it all down for you, not just the equation itself, but how it works in the real world.
And hey, maybe you'll even pick up some tips for acing your own technical interview, right?
Exactly. So it sounds like the candidate starts off strong, giving a pretty clear definition.
Yeah, saying it's all about energy conservation, basically, in a moving fluid. I mean, that's the gist.
They even lay out the equation itself, but I'll be honest, all those variables kind of make my eyes glaze over.
Uh-huh, I get it.
Yeah.
But you know what's impressive is they don't stop there. The candidate goes on to explain what it all means, like in plain English.
So breaking down those energy types, we got pressure energy, kinetic energy. That's the energy of motion, right?
Exactly. And then there's potential energy.
Yeah.
That depends on the fluid's height, all of those together. They got to stay constant along a streamline.
Hold on. Streamline. Not sure I'm following you.
Good point. Imagine like an invisible line showing the path a little particle of fluid would take as it moves.
Okay, so the fluid's flowing along this path, and even though pressure, speed, and height might change, the total energy stays the same.
You got it. You're picking it up quick.
Hmm.
The candidate even uses a roller coaster analogy to make it like visual.
Oh, I like where this is going.
Imagine the coaster zooming downhill, loses potential energy because it's lower, but gains speed, so kinetic energy goes up, right?
Yeah.
And you can feel the pressure change too.
Okay, I can kind of see it now. But isn't a roller coaster a little different? I mean, it's not like a closed pipe.
Yeah, you're right to point that out. It's a good analogy to start, but it's got its limits for sure. In a closed system, like a pipe, things are more contained.
Right, right.
But even with those differences, that main idea of energy conservation, that still holds true.
That makes sense. So it sounds like Bernoulli's equation works great in a perfect world, but didn't they say there's some conditions too?
Oh, definitely. The candidate correctly points out, for this equation to work, you got to assume a few things about the fluid.
Like what?
Well, first, it's got to be incompressible, meaning the density stays the same no matter what.
Okay, got it. What else?
The flow has to be nice and steady, no sudden changes.
Smooth sailing.
Exactly. And ideally, no viscosity, meaning no internal friction, like things moving along without any resistance.
So like no friction, no problem.
Pretty much. But the interviewer threw in a twist, bringing up that real-world fluids, well, they always have some viscosity.
Right, because we don't live in a perfect physics textbook, unfortunately.
Exactly. And that's where things get really interesting. The interviewer asked, how would you deal with that viscosity in, real-world applications?
Ooh, putting them on the spot. So how'd the candidate handle that?
Honestly, pretty well. They brought up the idea of head loss.
Head loss.
Yeah, it's represented by HL in the equation.
Yeah.
Basically, it's the energy that gets lost due to friction as the fluid's flowing.
And so like some energy is leaking out of the system because of that friction.
Yeah. And what's important is the candidate didn't just mention it. They explained how engineers actually use this to make the equation more accurate for the real world.
Right, because it's one thing to know the equation, but knowing how to adjust it for the messiness of reality, that's next level.
Exactly. And I don't think the interviewer was looking for that,
Yeah.
Can this person go beyond just book smarts?
To really get it.
That they can apply it. So far, we've been talking theory, but where does Bernoulli's equation actually show up in the real world?
Yeah, give us some examples.
Oh, there are tons. The candidate rattles off a bunch. Venturi meters, orifice meters. We got airplane lift, even measuring blood flow.
Yeah.
Hydraulic machines, too, like pumps and turbines.
Wow, that is a lot. I'm kind of curious about that blood flow one. Sounds complex.
It is. But at its core, it's still about that relationship between pressure, speed, and height that we've been talking about. We'll get into the specifics of all that in a bit, but first, let's zoom in on one example the candidate goes into detail on, the Venturi meter.
Okay, Venturi meter it is. What is that thing anyway? And how does it use Bernoulli's principle? Venturi meter, huh? Sounds kind of like a sci-fi gadget.
Not as fancy as it sounds. It's actually been around for ages. Basically, it's just a simple way to measure how fast fluid's flowing. Picture a pipe, and it narrows in the middle.
Okay, I'm
That narrow part, that's the throat. So the fluid's moving through the pipe, and when it hits that throat, it's got to speed up.
Right, because the same amount of fluid has to squeeze through a smaller space.
Exactly. Think of it like putting your thumb over the end of a hose. Water shoots out faster. Yeah.
Yeah, I get that. So how does this all connect back to Bernoulli?
That's the cool part. Remember, Bernoulli's equation says faster fluid means lower pressure.
So in that narrow throat where it's speeding up, the pressure drops.
You got it. Now you've got a pressure difference between the wide part and that narrow throat.
Okay, and that difference tells us something.
It tells us the flow rate, how much fluid's passing through in a certain amount of time.
That's pretty neat. I mean, the candidate even mentioned a specific formula for calculating that flow rate, right?
They did. And that shows they've really dug into the details. It's not just about the concept, but how it's actually used.
I'm starting to see how powerful this equation is. It's not just some theory in a textbook, it's actually used to build stuff.
Absolutely.
Yeah.
That's what makes it so exciting to learn about. It connects the physics to real engineering.
We were talking about airplane lift earlier, and I'm still kind of hazy on how Bernoulli and Newton's third law work together there.
Yeah, let's break that down. So picture that airplane wing again, curved on top, flatter underneath.
Got it.
That shape is super important. As the wing moves through the air's got to flow over both the top and the bottom.
Right.
Now, because of that curve, the air going over the top has to travel a longer distance to reach the back of the wing compared to the air underneath.
Ah, I see. So the air on top has to speed up to catch up.
Exactly. And what happens when air speeds up? Pressure goes down, thanks to Bernoulli.
So lower pressure on top, higher pressure underneath, and that pushes the wing up.
You got it. It's like the wing's being sucked upward. But wait, there's more. The wing's also pushing air downwards.
Right, which brings us back to Newton.
Every action has an equal and opposite reaction.
Yeah.
So pushing the air down creates an upward force on the wing. That's more lift.
So it's like a double whammy, Bernoulli and Newton tag teaming to make flight happen.
You got it. It's amazing how these seemingly simple ideas explain something as complex as flight, huh?
Totally. And the candidate, even mentioning both of them, shows, they're thinking about the whole picture, not just one piece.
It's about understanding how different concepts work together, right? Not just finding one right answer.
Okay, so we've got Venturi meters and airplanes. What about some of those other applications, like blood flow?
Another great example. Imagine a device that goes around an artery, kind of like a mini Venturi meter.
So you're creating that same narrowing effect inside the body.
Exactly. As blood flows through that narrow spot, it speeds up, pressure drops.
Yeah.
And by measuring that pressure difference, doctors can figure out how fast the blood's flowing.
So it's like a non-invasive way to check on your heart health.
Pretty much. It's amazing what you can do with this one equation, right?
Yeah, from airplanes to blood vessels, it's everywhere. But we've talked about how Bernoulli has its limits too, like with those thick fluids. What was the term again?
Viscous fluids. Think honey or oil. They've got a lot of internal friction.
So it's like the molecules are all tangled up, resisting the flow.
Exactly. And all that friction means energy loss, which Bernoulli doesn't really account for.
So for thick, syrupy stuff, Bernoulli's not the best tool.
It might give you a rough idea,
Mm.
but it won't be super accurate.
Okay, makes sense. What about turbulent flows? Why doesn't Bernoulli work well there?
Well, remember, Bernoulli assumes everything's flowing smoothly, nice and predictable. But in turbulent flows, it's all chaos.
Like trying to apply traffic rules to a mosh pit.
Haha, perfect analogy. The fluid swirling and mixing, changing direction. The pressure and speed are all over the place.
So Bernoulli, which likes things nice and orderly, just can't keep up.
You got it. For those situations, you need more powerful tools, like the Navier-Stokes equations.
Speaking of Navier-Stokes, the candidate said those are way more complex. What makes them so different from Bernoulli?
Well, for one thing, Navier-Stokes deals with viscosity head-on. Remembers those sticky honey molecules. It factors in all that friction.
So unlike Bernoulli, which pretends friction doesn't exist, Navier-Stokes embraces the mess.
Exactly. And it includes other forces, too, stuff Bernoulli ignores. It's a way more complete picture, but the math gets pretty hairy.
So it's like going from a hand-drawn map to Google Earth, huh?
Exactly. Both have their uses, but it depends on how much detail you need.
So viscous fluids, turbulent flows, anything else where Bernoulli might not cut it.
Oh yeah, compressible flows. Bernoulli assumes the fluid's density stays the same. Works fine for most liquids and gases at normal speeds.
But when things are moving really fast...
Then density can change a lot. Think about like a jet engine. Bernoulli just can't handle that.
It's cool that the candidate brought up all these limitations. Shows they're really thinking critically about when the equation works and when it doesn't.
Definitely. That's the sign of a deeper understanding. Not just knowing the formula, but knowing its limits.
Okay, so we've covered tons of applications for Bernoulli. Measuring flow, airplane lift, even blood flow. And we've talked about its limitations. Now, let's tackle that final challenge from the interviewer. The horizontal pipe with different diameters.
Ah, yeah. That was a clever way to see if the candidate really understood Bernoulli and the continuity equation. Remember that one?
Vaguely. So the challenge was to figure out where the fluid's moving fastest and where the pressure's lowest in this pape.
Right. And to do that, they had to combine both of those concepts.
Hmm.
So let's see how they did.
Okay, so we've got this pipe, and it's got wider and narrower sections. The interviewer wants to know, where's the fluid moving fastest and where's the pressure the lowest? Sounds simple enough, but I bet it's trickier than it seems.
Yeah, you got to really know your stuff to get this one right. And the candidate, they totally nailed it. They started by talking about the continuity equation. You remember that one? It's all about how the mass flow rate stays the same no matter the pipe size.
Right, right. So even if the pipe gets narrower, the same amount of fluid has to squeeze through in the same amount of time.
Exactly. And to do that, the fluid's got to speed up in those narrow sections.
Ah, like putting your thumb over the hose again.
Exactly. Now, here's the key part. The candidate then linked that idea to Bernoulli's equation.
Yeah.
Faster flow, lower pressure. Boom. Connection made.
So in the narrow parts of the pipe where it's speeding up, that's where the pressure is going to be lowest.
Bingo. They got it. And what's really impressive is they didn't just say the answer. They explained why, showed they really understood how those two equations work together.
It's like they're not just memorizing facts, they're thinking it through, applying the concepts. I wonder, do they think about how this applies to, like, real plumbing?
That's a great point. I mean, plumbers use this stuff all the time. They can change the pipe size to control where the water flows faster or slower, where the pressure is higher or lower.
So even something as basic as plumbing is using some pretty high-level physics.
It is. That's what's so cool about this. Okay, so we've talked about Bernoulli's equation, what it means, how it's used, even when it doesn't work.
Hmm.
And this candidate, they aced it. Showed they had a deep understanding, not just surface level.
Definitely. It's been awesome breaking this down. We covered a lot today. Venturi meters, airplanes, blood flow, even when to use Bernoulli, and when to reach for something more powerful like Navier-Stokes.
And remember, this is just one example,
Yeah.
There's a whole world of fluid dynamics out there just waiting to be explored.
Exactly. So to our listeners, next time you see a plane flying overhead or you're messing around with the garden hose, remember Bernoulli. That simple equation is at work all around us.
Keep asking questions, keep exploring, and who knows what you'll discover. They can change the pipe size to control where the water flows faster or slower, where the pressure is higher or lower.
So even something as basic as plumbing is using some pretty high-level physics.
It is. That's what's so cool about this. Okay, so we've talked about Bernoulli's equation, what it means, how it's used, even when it doesn't work.
Hmm.
And this candidate, they aced it. Showed they had a deep understanding, not just surface level.
Definitely. It's been awesome breaking this down. We covered a lot today. Venturi meters, airplanes, blood flow, even when to use Bernoulli, and when to reach for something more powerful like Navier-Stokes.
And remember, this is just one example,
Yeah.
There's a whole world of fluid dynamics out there just waiting to be explored.
Exactly. So to our listeners, next time you see a plane flying overhead or you're messing around with the garden hose, remember Bernoulli. That simple equation is at work all around us.
Keep asking questions, keep exploring, and who knows what you'll discover.